Hello, and welcome to my presentation on deep dimensional and multimodal emotion recognition using attention mechanisms. My name is Jan Lucas, and I'm a recent graduate from the Master University from the Department of Knowledge Engineering and Data Science. First of all, I'll walk you through the aim of this project. So the idea is that we want to fuse multiple modalities, in this case video and audio, using a fusion model for the prediction of emotion. And in this case, emotion is a two-dimensional model consisting of valence, which describes the positivity or negativity of an emotion, and arousal, which describes how intense or calming an emotion is. So for this, we needed some data. So we used the Ricola data set from the ABAC 2016 competition, which provides continuous labels per frame. So valence and arousal values for every frame of video. It consists of 18 clips, each 5 minutes long, consisting of subjects from speaking a single language, but from multiple cultures. And all of these clips have relatively consistent quality among them. And from these clips, we extract some features. So we rely heavily on pre-trained models for our features, using them as feature embeddings. So the idea is that the first layers of these big convolutional models provide means of extracting features, and we use the activations of these final convolutional layers as features for our own models. So for VGG face is used for our video features. So we extract the faces out of every frame of video and we feed it to the VGG face model. And for VGG-ish, we used a rolling time frame of audio to extract audio features with it. So for our model, we rely heavily on the DLSTM model, which was proven by Zhao et al. For emotion recognition. And basically it consists out of two LSTMs stacked on top of each other with a dropout layer in between. And finally, there's a linear layer which regresses the output of the LSTM onto emotion predictions. And this is the starting point of our own architecture, which I'll describe next. So we have audio embeddings and video embeddings for each time step with corresponding valence and arousal annotations. So for this, we construct a DLSTM for each modality separately. And then for video, we'll include something called embedding attention, which is something I'll come back to later. And for every time step, the DLSTM provides a prediction output for both valence and arousal. And we want to fuse these using their hidden states and a attention mechanism to provide the ultimate, the final emotion prediction. And I'll be focusing on these parts next. So first of all, we have embedding attention. So instead of letting the DLSTM consider every embedding sequentially, we wanted to be able to attend to a window of feature embeddings. So we want to divide our attention over a time window of features instead of looking at each of them in order. So for this, we compute a attention score for every time step using the following formula, where we take into account the current hidden state of the DLSTM and the contents of the embeddings. And then we apply softmax to these scores, and then we use these scores to construct a weighted combination of these embeddings, and we use that as input to the DLSTM. Our other method, the fusion attention mechanism, tries to fuse the outputs of these LSTMs for each time step by also looking at their hidden states. So for each of these LSTMs, we have a hidden state and an output for every time step, and we want to fuse these using attention. So before I get to the model we propose, we set two baselines to compare ourselves with. So the first is just linearly combining the outputs of the LSTMs like this. And the second is regressing the hidden states directly like this. And we will compare this with our proposed methods, which is bimodal attention fusion. So we combine the hidden states of these two DLSTMs into a vector by concatenation. And then we compute attention scores using these hidden states for each output modality. So we do this separately for valence and arousal. So basically we can attend to each of the DLSTM's outputs based on their hidden scores, their hidden states. Then again, we apply softmax to these scores and we output a weighted combination of the DLSTM outputs. So in order to validate our model, we propose a set of experiments. So first we want to see what the impact of embedding attention is. For this, we only look at the video modality for now. So we train a video only DLSTM and we train it with and without embedding attention. And we also try to see the impact of increasing the window size for this. In order to assess performance, we use a predetermined train test split, and we compute the CCC, which is the concordance correlation coefficients between our predictions and the ground truths. So we get the following results for this. So for arousal, there's only a very small difference, but for valence, we can see a slight increase in the performance with embedding attention. And in our case, video is the more performant modality for valence prediction. However, this difference is very small and not significant. And it should be mentioned here that in order to get embedding attention to work, we had to bypass it for the first couple of epochs because otherwise the model would not converge. So we first trained it for a couple of epochs without embedding attention and then add embedding attention to it. And this is possibly because of the cyclic dependency between the model input and the hidden state, because embedding attention provides the input, but also depends on the state of the model. And then second, we add an experiment for fusion attention. So we train the two DLSTMs separately, one for video and one for audio. So each of them tries to predict emotion separately. Then we freeze their weights and then add the different fusion methods to it in order to see how well they can fuse these two networks. So the results are as follows. In both the valence and arousal case, the bimodal attention mechanism outperforms the first baseline and is very comparable to the second. And for our last experiment, we try to compare ourselves to the state of the art. So we train a model using both the video and audio DLSTMs, and we apply embedding attention on the video modality and bimodal attention fusion as the fusion mechanism. And then we train both the DLSTMs and the fusion mechanism simultaneously. So no freezing of the weights as in the previous experiments, but we do it all together now. And this gives us the following results. Our proposed model is the bottom row, and as you can, and the baseline is the baseline provided with this data set, and the state of the art is the best method, the best performance on the data set so far. So in this case, we've outperformed the baseline for the arousal and get very close for valence. And the state of the art is also pretty close. The main point is that we get pretty comparable results, even though both the baseline and state of the art used a couple extra modalities. So they also included extra video modalities and a couple of physiological data, which we did not. So the main conclusion is that we were able to get comparable performance using attention-based mechanisms compared to the baselines. And for future work, we would like to look at the different training procedures for attention embedding. So bypassing the attention embedding might be detrimental to its performance. And maybe there are better ways of doing this. And secondly, we could try fusion over a temporal window of the LSTM predictions instead of only looking at the outputs for a single time step. Okay, so thank you all for your attention and your time, and I would love to hear any questions.